full person. Okay. So I'll be just discussing for a brief time that it's a totally new approach to the magnetism. So what we all know, very basics. So
Yanti, it's not full screen.
it is not full screen.
No.
It has to be. No, it is.
Yeah,
Ah.
now it is. Now it is.
Okay. Okay. Sorry. So today I'll be discussing about something which is just beyond the conventional definition of what we all are familiar with. What is ferromagnetism and what is anti-ferromagnetism? So, and before I get into that, I just would like to put a single question. So, whether and how an unconventional superconductivity or superconductor could be realized in magnetism. So, let me simplify this question. So, putting it otherwise, so we all know magnetism and superconductivity doesn't go hand in hands. I mean to say, we all know that it's called Mesmer effect. If you can bring a superconductor and put it in a magnetic field, it will actually repel the magnetic flux from its outer surface. Okay, we call it Mesmer effect. And why it is so? It is a basic superconductivity phenomena because of which it doesn't allow. But that superconductor, which is basically we all know as a BCS superconductor, Badin Cooper and Skripper superconductor, or you can call it S superconductor. S means it is spherical symmetric. That means the Cooper pair actually forming a spherical Fermi surface, or the band gap is actually spherical around the Fermi surface. That is why it is known as S wave or S superconductor. So likewise, here I have shown here in the picture, you can see this is superconductivity S wave. It is a Fermi surface representation. It is spherical in symmetry. Cooper pair actually forming a spherical geometry around the Fermi surface or gap. Likewise, there is also a wave called D wave superconductor. And the D wave superconductor actually here, the electron actually does change their momentum or change the sign of their momentum in this kind of superconductor, and we call it px plus minus iy, that is otherwise known as a D superconductor or a D wave superconductor. So generally the mechanism for this people have proposed may be due to strong electron correlations. So this is about the superconductivity. Now coming to the magnetism, the conventional ferromagnetism, we all know, it is electron and a hole pair, and the only difference is the density of the spin polarization of one or other types. Either it is electron or a hole, but the density of states for one will be different from the others. So that is coming as a net ferromagnetism in the material, or net spin polarization in a material. So the question is, can we realize the D wave superconductor counterpart in the field of magnetism? That is the question. So conventionally, by definition, we all know ferromagnetism actually is nothing but the long range magnetic order or long range order of the spin polarization in a material. And because of that spin polarization, system doesn't preserve the time reversal symmetry. However, if the same question can be extended to the anti-ferromagnetism, which is another phase of the magnetism or arrangement of the spin polarization, but in antiferromagnet, there exist two different types of sublattices, where in one sublattice, the spin polarization will be in specific direction with regard to the polarization in other sublattices. But the net magnetic moment or net spin polarization is zero. So here if one can ask, how about the time reversal symmetry breaking? The answer is there won't be any time reversal symmetry breaking in the antiferromagnet. Then one can further ask the question, can we realize a material where net magnetization will be zero, but still it can break the time reversal symmetry? the question what I have asked previously, can we realize the D wave superconductivity counterpart in the magnetism is very same of asking whether can I have a system or a magnetic material where net magnetic moment will be zero, but it can also break the time reversal symmetry. The answer is yes. And the people very recently in the year 2022, I have given the references. You can have a look into that. Though the authors have claimed that actually by using the non-relativistic spin split group symmetry, one can actually categorize the magnetic material into three different categories. Why three different? Because we generally magnetism people have categorized into two different classes. One is ferromagnetism, one is anti-ferro. Other are just nothing but a minute change in the moments value. Then you can end up with the other. But these are two very special classes of materials, that ferromagnetism and anti-ferromagnetism. But because of this spin group symmetry, they have categorized the entire material into three different classes. One is ferro, another is anti-ferro, and another one they are actually named it as alter magnetism. This is alter magnetism. What it is? It will have ferromagnetic like spin polarization. It can break the time reversal symmetry, but the net magnetization will be zero. That means it is the material which can harbors, or it is the hybrid of ferromagnet and antiferromagnet. The characteristic and the physical property of this material will combine the physical property of individual ferromagnets and antiferromagnets. So this is what the basic idea is, and the name they have given to these phases of the matter is known as alter magnetism. So first, if you look at the ferromagnetism, this diagram, these four things are very symmetric structure. That means if you consider there are four different atomic sides, the atomic spins arrangement are of equal uh, order or of equal size. That is why it is represented in a single color. Okay, this is the energy momentum diagram. If you can see this one, this is the energy momentum diagram, K vector, and this is the superconductivity representation. How the S wave this is the ferromagnetic spin, and you can clearly see this spin arrangement can break the time reversal symmetry because it has non-zero net magnetization, which is represented here. Okay, non-zero magnetization, and this is the spin group symmetry representation of this ferromagnetic material. Okay, that means this has a real space spin arrangement as well as momentum. This ek is momentum space electronic band structure, right? And this is your real spin structure as well. Likewise, if you see the antiferromagnetism, you can see these are nothing but the combination of two different sublattices. One is of this brown color or orange color, and this one is this violet color. Yeah, green, blue color. So, but these two different sublattices can be interrelated to one another or can be transformed from one to another by the symmetry operation of translation or inversion. Okay. Now look at this energy momentum diagram. Here there were two different things, but it is spin degenerate because the net magnetic moment is zero, and net magnetic moment is zero. This is the symmetric group representation, spin group representation. This is their energy momentum diagram. So if you just combine these two, you will end up with this. This is known as alter magnetism. And what does it say? Net magnetic moment is zero. You can say this is the physical property. This material has borrowed from the antiferromagnetism, and the spin polarization, you can see individual spin polarization. It has borrowed from ferromagnetism. That means magnetic order is there. And this is the energy momentum diagram. It is just a combination of ferromagnetism and antiferromagnetism. What is the gain then? Okay, we have observed this, or theoretically people have proposed it. And what is the big thing about it? The big thing is, this is what I have told you. It is written in the words, and these are the material. Now here I just want to tell you something. So generally, if you have seen, if you have slightest idea about the topological classification of the material, one direct semi-metal is of course always preserve two different symmetry. One is time reversal symmetry, one is space inversion symmetry. Let's suppose the first two-dimensional Dirac semi-metal ever discovered in the field of experimental physics, or even theoretically also, is graphene. So it is a two-dimensional Dirac semi-metal. Okay. So in that Dirac semi-metal, as I said, it always it has fourfold degeneracy at the band touching point, and it always preserve time reversal symmetry as well as inversion symmetry. So now the question comes: graphene is non-magnetic, but subsequently people got to know that it is, though made up of only the hexagonal chain of carbon atoms, it's still magnetic, and the region is totally different. It's beyond conventional explanation what people would have thought initially. However, if a question one may ask, how about if I am interested to synthesize in my laboratory a magnetic Dirac semi-metal? Since by definition it says Dirac semi-metal means it always has to preserve two symmetry, time reversal and inversion. But I need to make it magnetic. How can I make it magnetic? The moment I make it magnetic by applying the external magnetic field from outside, or by incorporating some magnetic element into the structure so that it can itself create the magnetic field internally, in principle it will break the time reversal symmetry. So in definition, I could not have, or anybody in principle would not be able to synthesize magnetic Dirac in the laboratory. In principle, magnetic Dirac semi-metal is not possible to realize experimentally. That's what the theoretical definition says, or a fundamental understanding says. However, people have come up with an alternative explanation. If I make a material ferromagnetic, it will immediately break the Kramer's degeneracy or time reversal symmetry, and I will end up with while I will never have a magnetic Dirac. But how about if I have a anti-ferromagnetic interaction in a Dirac semi-metallic state, or Dirac topologically Dirac semi-metal? The net magnetization is zero. Individual sublattice have non-zero net magnetization. However, in the entire system, the net magnetic moment is zero. That means entire system preserves the time reversal symmetry, but individually they may not. So in this way, I could have a magnetic Dirac, which is a very absurd state of physical states of matter, which is this is the another way to realize the magnetic Dirac topologically Dirac semi-metal, alter magnetism. First thing. Second thing is another important phenomena, but all the condensed matter experimentalists are aware of. It's very famous, and it is otherwise also known as the Queen's experiment in the condensed matter physics, known as Hall effect. So generally, Hall effect, we know, if you actually allow a current carrying conductor in a perpendicular magnetic field, you can of course always observe a perpendicular deflection of the magnetic charge carriers at the opposite end, which is perpendicular to the electric as well as magnetic field. But if you do perform the same experiment on a magnetic material, you will have a contribution from the magnetization, and we call it anomalous Hall effect, and subsequently people have explained it in terms of a Berry curvature, if at all it is of internal origin or of external origin. So it can be explained in terms of Berry curvature. So this anomalous Hall effect, if a system which has no net magnetization, in principle, you should not actually experimentally realize any anomalous Hall effect. But surprisingly, I just want to say here one point. So this is the prediction of altermagnetism. It's a very new domain of the magnetic phases of the matter, recently proposed and discovered. Ruthenium dioxide is the first material experiment. You can see I've written here, and the reference is this one. And this, the first author of this paper has extensively studied this field, altermagnetism, which is very new concept coming into picture. This ruthenium dioxide people have proposed in 2019, you can see, and 2020 people have realized it, and anomalous Hall effect. In principle, it should not have shown any anomalous Hall effect because it is a metallic magnet. So metallic non-magnet. So generally, if the magnetic contribution is not there, then why should the anomalous effect should arise? It should not have been. But surprisingly, it has displayed it, and the reason actually people have explained it. Probably the altermagnetic phase is present there. Likewise, spin current and at all. So now you can see there are a series of compounds people have proposed: SRREO3, Mn5Si3. So many materials have been proposed, but yet to be experimentally realized. Okay, so this is a very rich domain of the magnetic phases of the material coming to picture very recently, which is very encouraging. But what is more interesting, why did I choose this topic? Yes.
What was kappa in the previous slide? Kappa Cl. What was kappa in kappa Cl?
That is the insulator chloride. It is a insulating phase of the chlorine.
Okay.
It is a insulating phase. Exactly kappa, if you are asking, like our what I can say an example, tin, SN, tin. So generally it displays some topological feature in alpha CN. So it is a special kind of crystal structure arrangement.
Okay.
Like our alpha iron, gamma iron, FCC crystal structure. They have different crystal structure only.
Okay.
Okay. So just different crystallographic arrangement of the same atoms.
So alpha iron, gamma iron, and FCC iron have different crystal structure.
Alpha iron and gamma iron.
Okay.
Alpha iron, gamma iron, they do have different crystal structure. Though they are iron, but they do have different crystal structure. One is BCC, one is FCC.
Okay. Okay.
Like that only.
Okay.
But this is insulator. This chlorine, what you are talking, it is an insulator. What I mean to say here, as I said, in anti-ferromagnet, there are two sublattices in conventional magnet, but those two sublattices can actually transform from one to another by symmetry operation like translation or inversion. But in altermagnetism, the two different sublattices cannot be transformed from one to another in terms of any sort of this symmetry operation. But a special kind of rotation, six-fold, four-fold, or whatever, some sort of rotation may probably able to transform from one phase to another. Okay, the symmetry operation is rotation, not conventional translation or inversion. That's the difference.
Okay.
And yeah, that's the difference. And coming back to here, why did I choose this topic to present? Because in 2023 January, one PRL came on a material called MNT, manganese and tellurium. This is metallic, and as per the crystal structure, as per the band structure, the material should not have displayed any sort of a Hall effect. So, but surprisingly, it has shown spontaneous anomalous Hall effect. Sorry, spontaneous anomalous Hall effect, which is actually violating the conventional understanding what we understood so far. So that is why this is the first claim. You can see the material proposed here, ruthenium dioxide, ReO2. It is very much similar to that structure only, NiAs, nickel antimony, NiAs crystal structure. But why this is showing anomalous Hall effect? Here, the manganese atoms are arranged in a particular order. So it should have given ferromagnetic behavior, but the moment it give the ferromagnetism, then the material should have been magnetic in nature, but the material is non-magnetic. The MNT is zero magnetic moment. That is why they are calling it vanishing net magnetization. M equal to zero. I told you, na, in alter magnetism, the material which has borrowed one physical property from anti-ferromagnetism side is net magnetization zero. Zero net magnetization. If zero net magnetization is there, it should not have broken any time reversal symmetry. If it doesn't have broken and if it doesn't break any time reversal symmetry, then why should I have get some anomaly in the Hall effect? I should not have gotten it. But people have observed it experimentally. So Mn atom, then tellurium atom, followed by another Mn atom, like this. The arrangement between two magnetic Mn atom or between two manganese spin, there is a non-magnetic tellurium spin. Okay, that is why the net magnetization is zero. But this special kind of arrangement, the non-magnetic ion or atom between two magnetic atoms actually breaks one sort of crystal symmetry. And that is the reason why this particular arrangement of manganese atom, or you can call it in a technical term, the anisotropic crystallographic environment of the manganese atom in MNT system actually is the responsible for the observation of this spontaneous anomalous Hall effect, which is a totally new thing. And this is a semiconductor. It is not like a topological insulator or a superconductor, nothing like that. It is a semiconductor, but they are calling it an unconventional semiconducting phase. This is a very beautiful finding. People are claiming it. It has made some news now. And the origin lies in alter magnetism. That was the thing I thought of to just discuss, because I also know nothing about it. I just want to learn more on this, and this is it.
Thank you, Kanti.
Thanks.
So, does anyone has any question?
No, sir.
Okay.
I don't.
Fine. These things are very new to me also, so I could not understand much unless I also read that paper myself.
Prakash, sir.
Maybe I'll have
Maybe just one thing. In S wave, you said S stands for spherical, right? In D wave, what stands for D?
D means it is related to orbital only. S, P, D, F, these are related to symmetry. When you are studying the advanced physics,
Orbital wise. Okay.
When we are studying in intermediate level, we are remember that S equal to 0 is spherical, or L equal to 1 for P, like that. Na? Orbital angular momentum relation with respect to the principal quantum number.
Okay.
So that D equal to Px plus minus Iy. Na? So if you just look at high TC superconductor, and cuprates are belong to that only, D wave.
Okay. Okay.
I would like to add one thing to it. So maybe it's not true in this case, but when I speak of as PDF orbitals, so they were named. So they were named by some person. So these are okay. So the name is, let's say, S stand for sharp, P for principal, diffuse, and fundamental.
Yes.
I don't know why they
Yes, they are like that.
Okay. So is this the same? So is that the same as we use in 1s2, 2s2, 2p2? No.
It is Rahul bhai, very same thing. In one way, you are describing the spectroscopy or the transition among the different atomic level, energy levels. Here also you are explaining. You are explaining here the orbital, how the electrons are arranged around the atoms in the orbital way, in a particular orbital. But that thing, na, SAR principle, diffuse, this thing that you are explaining just to explain the transition of a different spectra from one atomic energy level to another. SAR principle, diffuse, fundamental, SP, DFG, and so many are there. In Jenkin White, all these things are there. The spectra of multi-electron atoms.
Okay.
It is same thing. It is related to the occupancy of the orbital.
Okay.
L equal to 0, 1, 2, 3, like that only. SPDF has come from that.
Okay. Okay.
Actually, the question was remain unsolved, and still today also, because whatever phenomena in condensed matter experiment people not used to explain in terms of Fermi liquid behavior, they used to call it due to strong electron interaction. Okay. Then as the theory progresses, as the technology advances, then people got to probe the material in much more finer details. Then people come up with some different nomenclature. Nowadays people are calling it topology, some are calling it Fermion, some are calling it the topological insulator or topological semi-metal or a symmetry protected topological state. But there is only one states of matter ever discovered in the entire history, is which is totally robust and which is topologically order material, that is a fractional quantum Hall effect, which is totally counterintuitive and it defies the common sense. That means how come multiple interaction or a huge interaction among a large number of electrons can fractionalize its mass and charge, and that's what it is.
Okay.
That's what it is. That's why, because in plus 2 or 10th school level physics we studied the quantization of the charge, but now as you progresses and studied more, you are telling charge can be fractionalized, and that fractionalization is happening because for multi-electron interaction. That is the only states of matter that is topologically ordered states. No other states have been discovered ever.
And did you also say that mass can also be fractionalized because of the interaction between electrons?
Yes, that's what they are saying.
Okay.
That's what they are saying.
Okay.
Fractional quantum Hall effect is that only. Mass and charge.
Okay.
Because that is the only finding where you can see the charge has been fractionalized, which is charge is much more fundamental, right?
Yeah, it is.
But still, that is the only states of matter. What I wanted to say here is the question people wanted to ask: whatever magnetism we know, it is just the arrangement of electron and holes. But if we can have the D wave superconductor, which is quite complicated with regard to the S wave, can we have the similar counterpart in the domain of magnetism? And they are saying yes, and this is probably altermagnetism.
Okay.
So which is the hybrid of both ferromagnet and anti-ferromagnet and protected by some spin group symmetry.
Okay.
It's a totally new concept. Maybe it will get the momentum soon. But that PRL paper is editor pick or something, I think. But Sir was telling, so I saw that. But it is written in the language of symmetry.
They have only the Sanomorous Hall effect.